Are you in the know when it comes to application attacks that affect system resources? If not, well, you're in luck because that conversation starts right now.
You're watching IT Pro TV.
Welcome back to Security Plus here at IT Pro TV. And well, today's episode, as I love to tee up for you, is all about application attacks that affect your system resources that can drain the strength and power out of your actual server or whatever it is that you're running. So we got quite a few of these things to run through today. So I'm gonna go ahead and jump over to Wes.
All right.
Where do we begin? Oh, I guess we should start with what the heck are we talking about when we say system resources? What falls under that umbrella?
Sure. This is what I call really the four horsemen of computing, right? Because, well, they can act like the four horsemen as well if you don't have them, right? That's the CPU. We talk about memory. We talk about network, and we talk about storage, right? When you don't have any one of these, your computing machine system, like Dan said, doesn't matter if it's a server, really doesn't matter if it's even a little embedded system, right? Doesn't matter if it's a workstation. We're going to have problems, right? Either services aren't going to be available that should be available, running contrary to the CIA, confidentiality, integrity, and availability. We're going to potentially corrupt information, right? If we have memory overflows, buffer overflows and stuff. That's the integrity part. And then you could potentially see things like just general system crashes. So there's a lot of different reasons why this might happen, but those are the four main resources that we're talking about.
All right. So now that we know what resources we mean when we say resources, how would this typically manifest itself? What are a couple of ways in which we would see this?
Sure. So one of the things that you might see is if you've ever launched Task Manager, right? If you're in the Windows environment, if you're in Linux, maybe you've launched something like Top. And you could see that I know that I have a certain amount of resources available within my machine because, well, I allocated those resources. And then you connect to that machine and you fire up something like Task Manager, and all of a sudden you know, well, wait a second, my CPU's pegged, or maybe not all at one time. Maybe my CPU's pegged, but my memory's fine. Maybe my CPU's pegged, but I don't have any disk I/O going on. Or maybe you have them pegged all the way across the top. Those would be a typical indicator if you know that machine, let's say for instance a DHCP server, right? There's not a lot of activity going on a DHCP server. It hands out its options and it waits 7 days to talk to you again, right? So a lot of times, unless you're in large infrastructures, your DHCP server shouldn't be utilizing a lot of resources, right? Now, you have to have baselines because if I say the same thing about a back-end database server, I might expect to see lots of CPU, lots of memory, lots of storage I/O, network activity, because applications are constantly talking to that, typically through your user interaction. So you also have to have that baseline. But those are the resources that we're talking. Other ones, not just resource exhaustion, other things like memory leaks as well. Now, memory leaks, they can happen. They might not even be an attack. Remember, not everything has to be an attack to run contrary to the principles of CIA, right? The confidentiality, integrity, and availability. I've had applications before. I know back in several years ago, I know Firefox, I know it's a good browser, nothing wrong with it, but it had something going wrong in it. When you would launch it, it would continuously consume memory.
Chrome just calls that normal operation.
Oh, well, this is true. Chrome just spawns, 60 sub-processes, right? And all you did was open
What's
it.
using 4 gigs of memory? Chrome, as it does.
That's right. Now, again, joking aside, they fixed it. It's not that way, and I can't even remember. It's Firefox 183,000, whichever version they're on, now. But they fixed it a long time ago, and it's not really that problem. So an application that's maybe had some bad coding, and again, it may be a bug in the system and a bug in the coding, could start to chew up all of your memory. So know resource exhaustion, the 4 resources that we're talking about, and know a little bit about what a memory leak is. A memory leak is just when an application is online, and what I mean by online, it's actively running in runtime, and it just keeps consuming memory. Like Dan said, I opened Chrome and I have an 8 gig machine and I've got 2 gigs left and I've only got one simple application open. That might be an indicator of maybe just a bad application, but it might also be an indication of things like a buffer overflow attack, right? So that could be indicators of compromise as well.
Gotcha. So the malware known as Chrome. Be on the lookout. Very dangerous. But it's not the only game in town, right? The drivers can also be a culprit in this as well, right?
That's true. So, when we talked about in one of the episodes, Dan, if you remember, we talked about things like injection attacks, right? We talked more specifically about a DLL injection, right? Well, DLL injections are when you're modifying the drivers themselves, but sometimes you do this for legitimate purposes, right? When we talk about driver manipulation, it's typically a very sophisticated attack. All right, this isn't something that happens from your script kiddies. If you remember what we talked about, the threat actors being the lowest on the run, they don't have a lot of technical know-how. This is probably not going to happen by one of them. It's typically modification of the functionality of a driver. And like I said, it has a legitimate purpose, but in the context of what we're talking about here, it's an exploitation of a legitimate process. Let me give you an example, right? When we talk about driver manipulations, two that come to mind and two that you need to be aware of on the exam. One is known as shimming, all right? I was talking to Dan before we started with this episode, and Dan, I know you've worked in the industry for a very long time, definitely run support and been a systems administrator in the past. And I was telling you, one of the things that we used to do is we would support legacy Windows applications, right? And we'd come into a new operating system, but we still had to image an older machine. Well, those drivers might not be functional, an application might not be functional, so what we need to do is we need to make slight modifications, little shims, create these little small libraries that perform some kind of action, and a lot of times it's done for backwards compatibility, supporting some kind of legacy API. Again, they do it in drivers sometimes to even talk to legacy-based hardware. That means you got a new system that doesn't really talk to the old device. So what they do is they put a small little bit of code in there, and it, like a door shim, right? It shims and it straightens it up, and that shim performs all the functions that the driver would be natively performing, but it's done for backwards compatibility.
So it's a stopgap.
It is. That's a great way to put it.
I've got this old machine. I need it to do this new thing. It doesn't support that.
That's right.
Well, we'll just put a big old Band-Aid on it, and there you go. Hey, it works. No, what could go wrong?
That's right. Until somebody exploits it, right? So there's also an avenue. That's right. There's also an avenue that it can be exploitable. What we used to do is we used to use some of the Windows deployment tools, right? And you would create these shims, and you could pick, like a la carte, what it was. What was the old device that you needed to support? And they would have a library of shims that for backwards compatibility on things that they weren't going to bundle in the new operating system code. And you could pick them up, you could bundle them, and you could put them in the operating system. And now we have the functionality that we want. In this case, if it's exploited, you're going to get the functionality that the attacker wants. So we definitely have to be aware of that. So that's essentially shimming, Dan. There's another one where you're actually modifying the code, right? And that's something known as refactoring. Refactoring is something where you're modifying the internal code. Now, you have to keep in mind, when we talk about this a lot in security, and I'm sure in your courses too, Dan, you've mentioned this, that a lot of the security techniques that we have are for legitimate reasons. But it's always a double-edged sword. What can be used in systems administration, a lot of times requiring elevated privileges. If attackers can get into it via those elevated privileges, they can also modify internal code. And unfortunately, what happens is the behavior may not change. However, it might change. And again, legitimate reasons to do that are for design improvement, right? If you're doing a little bit of code analysis and you're saying, hey, we want to clean up the code a little bit, right? That might be something that you're doing it for a legitimate purposes. However, like we've mentioned with shimming, if it's somebody that's doing it for malicious reasons, they could modify that code to perform their own functionality. Remember the drivers, and here's a key takeaway with a driver manipulation attack anyways. Know what drivers do. Remember, they take the high-level programming language and they translate it into something that machine-specific language that the hardware can understand, and that's how the communication goes. That's a very privileged thing. In Windows, it's the Windows kernel that does this. Inside of Linux, it's the Linux kernel that does this. So the kernel, whether you're talking about NT kernel, whether you're talking about the Linux kernel, has privileged access to the hardware. And if the attacker can slipstream something in there that can exploit that privilege, now we got things like privilege escalation attacks, and we could potentially take over control of the computer in general.
And it's super fun for the attacker. It's an oh-no moment for those that are trying to defend these things. So
that's right.
That's a really good one right there. The idea of refactoring, maybe it's very good camouflage for the attacker if they're able to get into the code of something, refactor it, make it do the exact same thing on the surface of what it was meant to do, but also do a couple other things as well for their malicious purposes. Let's move on to race conditions.
All right.
Because race conditions are a really interesting topic. It's kind of heady on how it works. A couple ways in which you can see this. So Wes, why don't you go ahead and just kind of give us the basics on race conditions?
Most definitely. So race conditions, that's this thing where what you end up having is you have a couple of processes. You have maybe two processes operating inside of a Windows system. And let me show you what I mean. So we've got a process that's running, right? We've got process 1 and process 2. Now, according to whatever the programmer's design was, process 1 was supposed to execute. Then the results of process 1 are taken by process 2 and executed. If you've ever worked in a Linux environment, I think one of the shows you mentioned this, Dan, when we're talking about things like command injection. You know how in a command prompt, I guess it could be a command prompt, it could be a terminal and a bash shell, right? Linux commands can be chained together. You can pipe them through and take the input from this command, pipe it out to that output out to another command. Think about that. Think about you creating that pipeline. All right, now think about your application. It's doing a sequential processing. It says, I take the output from process 1 and I input that into process 2 and it's finished. That's the way it's supposed to run. However, in race conditions, what ends up happening is maybe process 1 runs and process 2 says, I'm not waiting for you. I don't care what your results are. I'm going to go ahead and run. So we get some kind of failure. All right, or maybe process 1 and process 2 decide, yeah, we're going to run at the same time. And we get some kind of error. All right, some kind of failure. It could be denial of service, but it's not operating in the way we want to. Dan, you know, we were discussing this. We've discussed this in the past. You know, I know you have this. So we have both, I think, the lights in our kitchen, right?
Yes.
Where I don't wire these because I would definitely mess something up. So Dan, let me bring you into this one, right? You have that one where you have a light switch that in this position, actually we know both positions of a light switch should be up for on, right?
So you've got two switches that run the same light.
That's exactly it, right? But when I turn one off and one on, does that light turn on or off?
No, but it flips the circuit.
It does, right?
So that when now, even though this one's in the on position, if you turn this to the on position, this is now the off position, right?
Yeah,
Right.
exactly.
It's
you
super
see.
weird.
Exactly. You see there. And that's kind of an example of a race condition, right? The normal functionality of a light switch is up is on, down is off, right? But when you have two of those switches acting in tandem together to control one function, well, one overrides the other.
That's it. You get one that's in the on position. This is in the on position. You turn that to the on position and it turns it off.
Yeah, exactly.
It's like, what is happening? Just flip the thing until it goes.
And that's a classic example of some kind of race condition that could happen inside of programming. So be aware of just general types of race conditions.
All right. Race conditions, obviously very interesting. Like I said, a bit heady, but something we need to be aware of on how it's at least basically supposed to work. Let's move on to Talk To.
Talk to me, Dan. Let's hear it.
Me.
That's right.
This is a new one on me,
Yeah.
so I'm legitimately interested in what Wes has to say.
All right, so Talk To, we are never shy of acronyms in IT, are we? I would like to be the person that gets to make up these acronyms. So Talk To, time of check, time of use. All right, this happens a lot of times when you have shared assets, shared resources. So think about something where you're doing file sharing. This young lady here, she checks the file at 8:30 a.m., right? And that ST is just short for me saying state 1. That's the state that it's in when she checks it. All right, now this gentleman, shared resource, more than one person working with it, he decides that at 8:35 a.m. he's going to modify it. Now it's in state 2. Remember that the young lady, when she was checking it at first, she believed that it was in this current state. And then she makes a modification to it, and we have an inconsistency. That's running contrary to integrity in the CIA triad, right? Now we've got some kind of file corruption, data corruption, and IT is information technology. And if your information isn't in the state that you expect it, you've got an integrity problem here. So that's time of check, time of use happens a lot in your shared resources. Like that.
Oh man, this is definitely something I've experienced. I had some cloud data. I was making show notes, and well, two people decided to access the same resource at the same time and make some changes, and I lost that battle. It wasn't fun. We mourn the loss of those notes, but I recreated them, and we trudged on. That being said, let's move on. Talk To is obviously a kind of a pain, so I don't want to talk about it anymore. Let's move on to pointer object dereferencing attacks. I really like these because they can be quite dangerous.
That's absolutely right, because one of the things that they do is they could potentially allow access to locations in memory, right? So let's kind of talk about this, right? It's common in some programming language is, and the practice is that they use a pointer, if you will, to locate a memory location, locate that memory, right? That memory address and find that data. But then once that data is done, they dereference that location in memory so we don't get memory leaks, right? And another program could use that information. But if they dereference it and leave it open, well, then an attacker might be able to put their information in there. I heard one kind of attack was called use after free, a use after free vulnerability where memory it was released, but the container was still there. And if they find that in the code, they can potentially allow access into memory. And that could be some kind of code execution on certain occasions, or worst case scenario, it could be a denial of service and it causes the entire application to crash. And then by, proxy, any service or maybe server even that it's running on.
Yeah, it can get a little janky in there when you're messing around with instructions and what goes where and what are you supposed to run. If you can get some access into that, you can access to one of these dereferenced memory areas and slip your own code in and then go, hey, yeah, run that, do this. And it goes, okay.
Sure.
Man, programs are dumb. But what's really interesting about what, as far as attacks can go, are integer overflows.
Sure.
And this is how a system kind of deals with numbers. Is that correct?
That's right.
And if you give it something weird, you could get some weird returns.
Most definitely. I think of when we think of integer overflows, I think of any kind of memory. Look at memory in general, right? Memory is a location and it has a finite space that is defined, right? Well, once that space is defined, if you put more information than was expected, that information is going to overflow into unchecked portions of memory and can cause a problem. Let me show you just a basic example where something like that might happen, right? So let's take your basic binary. Just go back to binary, right? I've got two decimal values that we look and we see in calculators and stuff. We should be able to add them up. But I want you to think about the binary that it takes to store those two decimal values, 155, 101, right? They're 8-bit values. Let's say that memory location is only allocated for 8 bits. Well, if I add 155 and 101, I get 256. Well, that decimal number doesn't seem to be a problem, but look what the binary value is of 256. It's 9 bits. So if I have an 8-bit location, but I have 9 bits that I'm sending to it, what happens to the other bit? Well, potentially whatever the attacker wants to happen, right? So it could spill you over into unchecked portions of memory, potentially giving you access to those locations and the ability to run the code.
All right, well, there's integer overflows there. Obviously, that's getting into the buffer overflow, integer overflow category. These are some pretty sophisticated ways of attacking a system, and you have to have some know-how when it comes to how registers work and things like that. But that is the basics of how those integer overflows work, and it's a very important thing for us to understand that once you start spilling into different areas of memory, you could potentially then gain some access that you don't normally see. So that being said, I know you got a couple of things you want to show us before we wrap this episode up.
Yeah,
A couple of
sure.
demos, just kind of get our feet wet and taking a look at some of these types of attacks.
Most definitely. We've got something up here from Lightning Security. Just give you a real quick demonstration of a race condition. And we'll go ahead and make sure that we leave the links here. This is Lightning Security. Got a cool little demonstration here of race conditions if you want to see. All right. Now, I'll go ahead and kind of just talk through some of this. Essentially what you're doing is you have your account balance and a friend's accounts balance here. And what you want to do is try to see that if you can get more money into one of these accounts, whichever side of the tracks it's on, then is supposed to be allowed. So
I like how it says it should have quotes around
your
friend's
friend,
account.
right? One and only brother from a Nigerian mother in a third world
exactly
country. That's right. So we're going to go ahead and we're going to send from my balance here, my account balance, to my friend, like Dan says. We're going to send $75, and we're going to go ahead and we'll send, and then we'll refresh the balance. Now, when we let me try it. Maybe I didn't click it good enough there.
You know how Macs do. There it goes.
There we go. All right, so send to friend, and notice I have $25 left, right? Well, if I try to send another additional $25 and refresh the balance here, notice that it says not enough money. But if let's do $15, and I send to friend, and let me see if I refresh my balance. Now I'm down to 10. Now I'm gonna click this a couple of times. I'm just gonna click it a whole bunch of times and see what we get here, and I'm gonna refresh the balance. Oh, it's still not doing it.
Send it faster.
Send it faster.
Yeah, that's a race condition, right?
Faster. We'll see how fast I can push that button.
You don't have $15 to send. You got to do like
10.
Do like $9.
I'll tell you, we'll do 9. There we go.
Do it fast.
No, Oh, there we go.
there we
There we
go.
go. I sent negative amount of
Right.
money.
So you
That's
sent
right.
more money than you actually
than I actually had, right?
Race
and I
conditions.
wasn't clicking fast enough. And
Gotta
there we
get
have
quick.
a race condition here, and unfortunately, my friend now has more money than was actually in my
Right.
bank
So
account.
if you owned both of these accounts, you now just made off with $8.
That's right.
Right.
That's
So
right.
if you were able to manipulate this to a higher amount, then there you go.
And if Wes could click a wizard faster, I could have had more money.
There you go. Well, there you go. Race conditions, and not just those. We walked through quite a few different attacks today. We looked at resources and memory, as well as driver manipulation, integer overflows. Race conditions were a lot of fun. Don't forget those dereferencing attacks. Very cool. And integer overflows as well. That being said, we are out of time for this episode, but plenty to come in our Security Plus series, so we look forward to seeing you there. Until then, have yourself a great day.
Thank you for watching IT Pro TV.